Okay, so now I'd like to make some islands. I'm going to go ahead and copy this step and then go over to the script and find a new line here at the base and paste it in. And so partly because my throat's pretty sore and partly because this is week 10, I'm just going to write the function directly here and do this a little bit differently than the kind of the two-step process that we've done in the past. Let's just write this function and apply it without testing it a lot first. We'll test it when we apply it. Is that okay? So here's the idea. I'm just going to say, let's make a function that is going to take this binary image and create vector objects, right? So it's going to take an image as a variable. It may take more than that, but to start with, I know that I'm gonna need to work with images or an image. And then I'm gonna do my curly brackets here because the function always needs to be contained kind of as an object, as a curly bracket object. And so what I'm gonna do here is say, well, the first thing I'm gonna need to do is I'm going to create a pixel area image, and that's going to be equal to I'm going to create a container called pixel area, and that's going to use the pixel area kind of method of images um, that is going to basically create an image where each pixel stores its area value. Is that fine? But then I want to make sure that the units are not in square meters because I think it's silly to be talking about regions in terms of square meters. So I'm going to make sure that we divide that, and I'm going to make sure that I hit zeros 6 times, right? A 1 with 6 zeros is going to divide by a million because that's going to convert square meters into square kilometers. It's going to represent now each pixel is going to be storing the area that it represents in square kilometers rather than square meters. And then I just want to rename this area square kilometers so that I kind of know what this image represents. Is that fair? So that's kind of step one. We've gone through this process before, but I'm just going to kind of, I think we did it last week in the Hanson. So, but I'm just going to kind of do it this way for now. So then I need to create something called land objects. And this thing is going to take an image. And the first thing that I want to do is because this thing that we made, remember we had to kind of apply this self mask to it so that it was just islands and not ocean. I don't want to create objects around all of the oceans and bays and inland lakes that I may have created by lowering the sea. I just want to focus on the islands, on the land. So the very first thing I'm going to do is say self-mask this image so that I'm only going to be creating vector objects, like only going to be creating features around discrete contiguous clumps of land pixels. Is that fair? And so then what I'm going to do is say, all right, now I need to add some bands to this image uh, because what we are eventually going to be using is the reduce to vectors method that we've used before. And so let me just go to it. It's over here and reduce to vectors, which converts an image to a feature collection by reducing homogeneous regions. Given an image containing a band of labeled segments and 0 or more additional bands, it runs a reducer over the pixels in each segment, producing a feature per segment. So the idea is that the first band is going to be this binary of a 1 and or nothing. So it's going to use these to define the features. The other bands that I add to this image are then going to be like dough bands that I'll be able to summarize with the feature cookie cutters, if that if unless you're never really like that metaphor. But the idea is I want to kind of feed it a couple of additional bands here to get some attributes associated with each feature. And the attributes I want associated with each feature are going to be the number of pixels and then the area in square kilometers. So to do that, I need to say I'm actually going to feed it itself, but I'm going to rename this one to be number of pixels. And then this has to be, I think, a part of a list. And I'm going to feed it another one too. I'm going to feed it the pixel area, which is already named area square kilometers. So what I'm hoping that it does is when it creates these features, it's going to create two additional properties. One, it's going to give me the sum of the number, like basically one, it's going to be the number of pixels that are contained in each island, and the other is going to be the area. And I'm using number of pixels as a kind of a it's a little bit of a crutch here to get to be able to get a unique integer ID of each island. But don't worry about that too much. And so then once I have that set up, I'm going to say reduce to vectors. And now I'm going to use reduce to vectors so I can just grab all of this business because this is the dictionary I need to write. So reduce to vectors, there's my parentheses, here's my dictionary, there are all of the um, uh, arguments that I'm going to have to feed this thing, and I'm going to do it in a dictionary style. So the reducer, I want to use the EE reducer sum. And we can go look in the tray, but I'm pretty sure that's going to call a reducer that's going to sum in each image, basically in each of these objects. It's going to sum up the number of pixels and it's going to sum up the area. Is that all right? So then for geometry, and this is maybe a little bit confusing, but we're going to be reducing these guys to a to features, and geometry here is really asking you about your study region. So I'm going to say geometry as my study region. Um, for scale, I'm going to basically want the scale to be whatever the scale of this image is. But the reason why we're writing this function is because we want to be able to use it not just for the Pleistocene case, but also for the current conditions, which you're going to do in Act 2. And the image in the current conditions is a different resolution than this image. So I'm actually going to make this another argument that we can define when we run the function. So then 8 connected, I'm going to say, oh, so sorry. So for geometry type, I want this to be a polygon, and it has to be a string. For 8 connected, that's about, do you want diagonals to count as connected, or do you want, if something is only connected on a diagonal, do you want it to not be considered a single object? And I'm going to say true for that. That's fine. For label property, I'm going to say, please use land. And then for CRS, I'm going to say, let's grab the CRS from the image. So if I type in this image projection CRS, it should, for whatever image I'm calling this function on, it should grab that CRS for it. For these two, CRS transform and best effort, don't have to worry about them right now. So I'm going to just highlight them out. For maxi pixels, I'm just going to go to the max that I think it'll play with, which is 1E12. And then for these two, I'm also going to just say let's not worry about it for right now. And that's great. So that's going to convert this image to vector features, and it should also tell me the number of pixels that are in each feature and the area of each feature. So I'm almost done defining my function. What I haven't done yet is kind of kick anything out because these are both internal variables. So I'm going to say now return, meaning like make the output equal to this guy, but then I want to sort, if possible, by the number of pixels. Uh, Sorry, didn't quite grab that, but if I say number of pixels, and then if I say false, that means the sort method, which is you can look at over, um, sorry, that's a feature collection. So it's in, uh, that's an image. So this thing should be a feature collection. And so when you use sort, you define the property and then whether or not you want it ascending. So if you wanted to go ascending from smallest to largest, then you could just not say anything. But I wanted to go descending. I'd like the largest land object to be the first one in the collection, and that should do it there. And then I'm just going to wink at that. And I think that is pretty good. So let's test this by trying to apply it. So I'm going to say apply the function for the Pleistocene land binary. So I'm going to say make islands, right? Because that is that's the name of this function that we just defined there. And it's going to take an image. So it's going to take the land Pleistocene image, this one. And then I need to tell it the scale, and I think the scale is 1,000 at the equator, so we'll just say 1,000. And hit run and see if it breaks. And it looks okay for right now. It's zooming way out. And is that because I have that set up too high? No, anyway, maybe that is something I did. Okay, so it didn't break. And then let's go ahead and print this. How many islands are in this thing? As just a quick check, you'll notice that I went back and um, commented it out to print Jebco just so that I don't. Okay, so I got 25 islands from this check, and let's go ahead and display them. Map, kind of add layer, and this should be islands, Pleistocene. I'm not going to worry about that, and I've asked you to display that name, and I'm going to do this false by default. So they're there if I want them. And so this will be a test because if we printed out the size and it worked, it should be fine. And now if I look at this and say, show me the Pleistocene Islands, there they are. So it looks like it worked. Is that fair? And I'm going to hit save here, and I'm just going to kind of go back to so that you have all of this on your screen in case you did a typo or something didn't work. But we're looking at 25 there, and you should get islands basically tracing over everything that was white. Is that fair? So that's that.